Okay, welcome. So on the other stage, people are currently looking at engineering gone wrong. Well done, Inspector. So I thought I would start today. First of all, let me say a little bit about myself. I work for Cisco. We do video conferencing, and I've been active in kernel development for almost 50 years. My God. Mostly doing video capture and anything related to that, so that's why your Android phone probably has some code that I wrote. But let me start with showing some good engineering, some really brilliant engineering. Voyager 1, launched when I was 8 years old. It's currently at 21.14 billion kilometers from Earth. It's truly amazing. And it is still communicating with Earth. And it has actually two different speeds. One is a 24/7 communication at 160 bits per second. So that is low speed telemetry, status information. It just goes 24/7, it goes on all the time. Some experiments that they are doing, they produce data at a higher rate, and it's stored on a tape, magnetic tape. And every so often that tape is transmitted, the contents of the tape, and that is done at 1400 bits per second. It can't go any slower, because that is the slowest speed with which they can drive the tape. And it is expected that sometime this year, the distance will be too great, and they can no longer receive that information from Earth. So they will shut down that experiment. Now, this is real engineering. I wish I was involved, but then I was 8 years old, so what could I do? So, this is CEC. 400 bits per second at 1 meter. It's embarrassing. So what is CEC? Stands for Consumer Electronics Control. It's an optional part of the HDMI cable. It's a single pin in there that transmits CEC. And it's basically a bidirectional bus. Well, it gives a little bit too much honor to call it a bus. It's a hack. I would call it a hack. And the basic idea is that you can figure out what devices are in the chain between your, say, set-top box, or in our case, video conferencing equipment, towards the TV. So you may have other DVD players, audio-video receivers, the TV itself. You can figure out what's there, and you can control it to a point. Basically, I became involved in this because we've been doing CEC for quite some time, but it was very basic, just turn on and off the monitor or the TV. But we wanted to do more with it, and our hackish implementation that we had needed to be turned into something proper. And since it was kernel co-maintained with the media subsystem, it was a perfect opportunity to write a proper subsystem. So since, what was it? I think 4.9 it came in staging. Linux has CEC support. There's no support, no framework for this in either Windows or Macintosh. We're the first and the only. Yeah. So it's using a single pin of the HDMI connector. It's optional, you don't have to implement it as a device manufacturer. It used to be high-end. These days it is fairly common, actually. And it provides high-level control functions. It's actually based on a very old SCART connector. I have no idea if they were ever used in the Ukraine. I've added a picture just in case you've never seen it. This is big, bulky, ugly connectors. I have no idea why they made them so big. That's a mystery to me. And they just took it and put it in the HDMI standard. They didn't take the high-level protocol. It is more they took the electrical stuff, and that's why it's so slow, I guess. And they made a new high-level protocol on top. Because it is so slow, you can't really use it for things like a firmware update, so you're limited to 1 header byte and 0 to 50 data bytes, that's all you get. And it's extremely slow. You can type faster than CEC is running. It's sort of, I'm probably maintainer of the slowest bus subsystem in the kernel. I think serial port can go slower, but nobody has been using those really slow speeds in decades. So I have a dubious honor of, well, it's relaxing, let's say. There are 2 types of addresses that CEC uses. One of them is the physical address. It actually defines in the hierarchy where the TV is at the top, where your device is. So we have several levels, up to 4. TV is always 0.0.0.0. Then you get 1.0. So you're populating, you're going down as your hierarchy deepens. The physical address is given by the EDID. So you hook up your, say, your laptop to the TV, and the EDID will contain the physical address assigned to you. If you have a TV with 4 inputs, the first one will be the 1000, the second 2000, etc. And if you're a repeater, so you have your own inputs, you will add that extra layer, and you have to update your EDID to correctly represent that to whatever is connected to you. FF is special value, means I don't support it, invalid. Also, when you get too deep, you will no longer be able to use CEC on the lowest devices. Then there is also a logical address. I have to say, these names, they're all very fancy. Address, you sound like an IP address. It's not. It's basically a nickname in IRC. You know, I want to be Verkuil if it's already in use because I'm logged in somewhere else, I get some variant of it. It's the same here. They made a number of logical addresses. So if you're a playback device, which is typical, you start out trying to claim address 4, but if someone else is using it, you will go on to address 8, playback device 2, then you have playback device 3. If they're all in use, you can use the backups, which are literally defined as, God, if everything else fails, you can use these, I give up. The protocol is old, it's hackish, it's a committee product, and it shows. It's not how you would define it today. And the probable reason for why it's so slow is that originally it was designed as a microcontroller that was sampling the bus, literally sampling the bus, no interrupts, no nice stuff, but about once every tenth of a millisecond or 100th, whatever. And that's how they would do it. So they were limited with the technology, and that's the reason it's so slow. Why they didn't change that when they moved it to HDMI, I do not know. It's really insane to have, say, an HDMI 2.0 4K cable where data is flowing around at 600 megapixels per second, and then you have this slow bus next to it. It's weird. So this is a fairly extreme but possible example of how it's used. TV at the top, physical address 000, logical address is 0. And then you connect it to a recording device, AV receiver, whatever. And you can all detect it. Any device here can detect what else is in the topology, and it can say you shut down, you become the active source. It's actually quite nice within the area that it was designed for, which is basically, let's say, home theater. As I said, if you want to do something fancy like upload the firmware, this is not the bus for it. Won't work. For no reason that I can think of, all the various vendors chose to give it a different name. So Samsung is calling it AnyNet, Bravia Link, Eurolink. Don't ask me why. The only reason I can think of is to terminally confuse the consumer. But it's really all CEC. So, at the end, for the last 10 minutes, 10-15 minutes, I want to give a demo. So it's useful to know a little bit about the electrical protocol that they're using. Every packet starts with a start bit. So you have, it's about 3.7 milliseconds that the bus is pulled low. Then it's pulled high a bit, and then the data starts. That's how you detect that a message is coming in. Logic 0, logic 1, the only difference is the total period is the same, but for logic 0, the bus is low for a longer time than for logic 1. Then the bits are grouped together. You always start with a header block. You have an initiator address, that's the logical address, so a TV that sends something will put in 0 there. Destination address, that's the device you're sending it to. Or this FF, and then it's a broadcast message for everyone. End of message, that is set to 1, if it's the last byte in the packet. And you have an acknowledge bit, and that is if you send it to a device, the device will acknowledge that it received it correctly. If it's not received correctly, you're supposed to do a retransmit. For broadcast messages, it works a little bit different, but I won't go into detail for that. So, why do you want to implement it? CEC is subdivided into features, which is basically different feature sets that a typical home theater system might want to use. The ones in blue, they are features that Cisco, we tested well. The others have only superficial testing because we are not using them. It's not relevant for us. We don't do TV tuning. But if you would be a TV manufacturer, you would implement that. So one touch play, that's ideal. It's the same thing when you start a DVD player and it automatically turns on the TV and everything. It's fantastic. System standby, puts everything into standby. You have recording support, timer programming for your recorder, deck control, tuners, device menu, very limited possibilities there. Remote control pass-through, that's very common, so you use your TV remote to change the volume on your AV receiver or vice versa. Audio control allows you to control AV receiver for audio. OSD name, I'm going through this fairly quickly, you can look it up later, but just to give an idea of what is going on here. You can give the TV a name, so you can say I'm a Cisco product and it will show Cisco. It's a device on and off. Routing control, so if you start to play back something and you have HDMI switches in between, they will automatically switch to the right input. Basic system information. The last one is important for us, that we can just create what is your latency. So the time between sending, that we send a video frame and that you actually display it, because we need to offset that for audio, so to give you audio delay. I'm really surprised how rarely this is implemented. I would say that this is ideal for AV receivers. I remember having to do it manually, to set up the delay manually in my AV receiver, when you can just ask the TV, but many do not implement it. Vendor-specific commands, audio rate control, I never understood why you would want to do that, but apparently some do. Audio return channel, that's fairly popular for the mid and high-end TVs, where you can send audio to the TV and it is returned through the audio return channel to your AV receiver, for example. There are other possibilities there, so the audio flows in the other direction as well. You need CEC to configure that. It can also be used for Ethernet, called HEC. Almost nobody does that, because everybody these days uses Wi-Fi. So the need to use an HDMI cable to set up Ethernet is pretty much done. Which is good because it's an absolutely horrible protocol and you really do not want to use it at all. So I had the opportunity to make this subsystem from scratch because there was nothing there. So that actually took a very long time, on and off. One of the biggest issues was that this protocol is a hack. Basically how you should look at it. So there are lots of little oddities, little special rules that you have to take into account. If every application would have to take care of that, nothing would work. So what I wanted is that all these rules, all these special things would be done in a framework as much as possible, so that life for an application would be much easier. And it took a long time to, I think I went into version 20 whatever, or at least into the early 20s before it was merged. And the difference between the first version and the last version is huge. So you get a CEC device. One thing aside, so a lot of Android devices support this as well. And they all use custom drivers, custom API or proprietary. So this is the first time that you have an API that is standardized and that everybody can use. And I really wanted to get away from all those custom things. It's horrible. How much control user space can get is a little bit up to the driver. If you want to, you can do almost everything inside the driver. If for whatever security reasons you want to do that, you're able to. Most of the time, the driver or the framework takes care of all the basic commands, of all the basic functionality and the special rules. And user space, for example, setting the physical, connecting the EDID and reading out the physical address is done automatically for you. In some cases, user space can do that as well. I'll show it later. Drivers just implement low-level CEC operations, so transmit, receive, view, setting up physical or logical address. Framework deals with all the rest. So messages, you can send a message and the reply can come in out of order. The framework will take care of that. You don't need to think about it. Core messages, like what is your physical address, return it, it's done automatically, the core knows it, so why would you do that in user space? A lot of work went into monitoring. So if you want to debug with a device, it is great if you can monitor all the messages coming in and out. Core code drives media CEC to either read out or fill a CEC packet. I have made a header with lots of static inlines to do that for you. You can just include it and use that to set up all the packages. It's dual license to BSD and GPL, so if you just want to use it on the BSD system or in user space with a BSD license, you can do that. For the remote control pass-through, you can optionally also integrate with the remote control subsystem of the kernel. Basic API, a lot of IOPTLs, get capabilities, what can you do? Get set physical address, get set logical address. It's plural. You can, a single device can claim multiple logical addresses. So if you are a recorder and if you're a TV with recording capabilities, you can expose both logical addresses. There are limitations. Not all CEC hardware can do that. A lot of them support only a single logical address. So when you go there, you need to ask an expert, I think. Setting the mode. It allows you, for example, to get exclusive access to the bus, so nobody else can send messages while you're using it. Read the manual. Receiving and transmitting. One thing that I found really wanted to get in, and that is working great, is that when you transmit, you can optionally wait for a reply. So a lot of messages are You send something and you get a reply back. It is great, especially due to the asynchronous way CEC works. And if you want to just do a quick test, you just send a message, you just wait for the reply, and you show that. It's ideal for testing, for experimentation. Great feature, actually. We have event queue, event handling, so when someone unplugs the cable, the physical address becomes invalid, the logical address becomes invalid. You need to know. Same when you plug in something, the EID is read, it will find the physical address, you will get an event telling you this is your new physical address. Debug FS, we have two status that shows basic status information of the CEC device adapter. That's always there, and then error injection, and I will come to that in a few minutes. I'm skipping this slide. If you ever need to really implement CEC, you have to read this. So just go back to the slide deck as posted and check this, because there are some nasty issues with hotspot detect in certain TVs. I put in a lot of attention to utilities. So there's a CEC control utility. It allows you to send literally any CEC message and receive it and monitor and whatever. It's a Swiss Army knife. It also supports a CEC extension for hotel displays. Just because I could, basically. Low-level CEC analysis, I'll get back to that in a minute. I have a folder that allows you to emulate yourself as a CEC device for debugging. So you're still prototyping, you don't have it yet. You can use the folder that you can act as an AV receiver, for example. And very important, we learned this from the media subsystem compliance tests, making sure that everything works. And this can test both the local implementation, more importantly, it can test remote implementation. So you can test if your TV actually complies to the CEC standard, or not, usually not. Current status, Pulse 8 dongle, if you're looking into set-top boxes and you want to use CEC, you quickly end up with that adapter, it's supported. Lots of SFCs are supported. Several receivers are supported, video receivers. We can do CEC over GPIO, and I will show that in a minute. Brand new for 4.17, just merged 2 weeks ago or something, is error injection support. It actually passed the official compliance tests, thanks to Synopsys, who did that with the official equipment, certified equipment. He found a single bug, well, small corner case. Pretty pleased about that. There are a few drivers in development. The one I really want to get in is DisplayPort CEC tunneling. So DisplayPort devices, they have an extension that allows you to convert. You need to have a DisplayPort to HDMI adapter, like this one. And you can actually use the DisplayPort extension to control the CEC bus. This is interesting because neither Intel, nor Radeon, or AMD, nor NVIDIA support CEC in the graphics cards, in the GPUs. I don't know why not, but it's available on almost every SoC, but not on graphics cards. So the only way I can use CEC on this laptop is by using the right adapter and then this protocol. I wrote a driver for it, there were comments, and I need probably have 1 or 2 days of quiet time to figure out the final issues and hopefully get it upstream. Because you would have the insane situation that it works, CEC works for DisplayPort, but not for a native HDMI output. Demo. So if you want to use CEC and you want to get a cheap debugger, so this whole setup is about $100 US. It's a Raspberry Pi. That's one, the main block of the expense. And you can buy a pass-through HDMI breakout box, a breakout connector. So that's another 35 for the Raspberry Pi, another 30 for that connector, and a breadboard and a few wires in your set. The idea is that you can sit in the middle. So you can connect from your product to the pass-through breakout and then from there to the TV. And you can use the Raspberry Pi to monitor the CEC bus. So the CEC pin is the brown wires. They connect to GPIO pins. I use two. I don't need to, I can use a single one, but it is very convenient to use two GPIO pins because one I can use for monitoring, and then an interrupt is used to monitor when it goes high and low, so I get very precise timestamps. And the other one I can use to send messages and actually actively communicate with the bus. The blue lines, by the way, they are hot plug detect, because if you want to do serious debugging, you want to know the status of those pins as well. But they're optional, you don't have to do it. In this case, so I have it here. I don't have anything connected, but it is enough just to have these two GPIO pins, CEC to GPIO pins connected. Because they can talk to one another, that's all they need. It's basically a little, they talk to one another, and it works. And this is all GPIO based. Most of the time, CEC is implemented inside an IP. So you basically say, here's my command that I want to transmit, and the IP inside the SoC will turn it into the low-level bit patterns. But you can also use a GPIO. The problem is, of course, to really send it reliably, you need something like real-time Linux. It actually works pretty well without. So for debugging testing, it's perfectly fine. There are certain situations where you have a slightly higher chance of wrong packages. I don't have the time to go into details. One of the great things about using a GPIO is that you have full control, so you can do error injection. So in our case, we use several SoCs with different CEC implementations, but we also have an FPGA, where we have our own FPGA implementation. So we wanted to test it in all sorts of error cases. And it is really amazing how much shit you can get with a single line. So to come back to here, so the first one is the start bit. So it can be, the pulses can be too short or too long. The same as the bits themselves, they can be too short, too long. You have to be within these margins. So what happens if you're outside the margins? What happens if two devices start sending at the same time? There is an arbitration mechanism. But that's of course very hard to test yourself. Very difficult to get two devices to send the same message at the same time. What happens if instead of, you're supposed to send no more than 16 bytes? What happens if someone sends 200 bytes? What happens if there is no end of message? What happens if, there's a surprisingly large number of error situations. And the error injection turned out to be a fantastic project. My colleague, who was working on the FPGA implementation, I drove him crazy, because every time I added a test, it failed. So we had to dig in and figure out what was the bug. Great for our product, but he was less pleased. So, okay, perfect. So I actually wrote the script. This is available in a branch of my project. We want to put this into the vFREL utils repository as a standard environment, but it's not quite ready yet. Oh. So what is happening here now, these two GPIOs, basically two different CEC adapters, they're talking to one another, and I'm generating all different error injection cases. And it is testing that the other side is actually reacting correctly. This is wholly automatic. At the end, you will get a list of pass and fails. What I would really want to do is that I can use this to test, for example, a TV implementation. The problem is why I can't do that quite yet is that there are certain error injections where there are different options that the device has on how to react. For example, especially when you have bit periods that are too long, the spec doesn't say anything what you should do. It tells you what you should do if it's too short. You need to send an error pulse. When it's too long, it makes no mention whatsoever. The only thing you can do is to time out at a certain point. But where that certain point is, nobody says anything about it. So this works. Well, it's easy, of course, because the same driver is talking to itself, basically, so this is not a big deal. But you can get a good idea of, so I start with a simple reference, just standard message, just to check that that works. What happens if you do a not acknowledge of the first message? You need to get a retransmit. Does that work correctly? The low drive, that is an error injection, so that's an error pulse. It signals to other devices that, hey, I'm hopelessly confused. Stop sending, retransmit. The arbitration lost, so basically what it does is you send a message. If you have enabled this error injection, it will immediately send another message back with a higher priority. I can only do that because I'm using a GPIO pin here. But it is fantastic for testing this condition because otherwise it's very, very hard to verify it. What happens if there is no end of message? You just stop. So I have lots and lots of different error cases. And so there is an error injection file in debugfs where you can basically send a whole lot of commands just using echo or whatever to the device, or send a script even. You can just combine it in a single text file. And you can control exactly what is happening on the bus and what sort of error conditions you want. It's very convenient for scripting. It's frankly been a lot of fun developing this. And what the script does when you run this, you also get .pin files. So this along the CEC CTL, we can record exactly what is happening on the bus. Let me just get one. It tells you what the physical address was, some time information, and then it's basically just timestamps and a value next to it. So 0 and 1 are when the CEC goes high, and 0 is when it goes low. And you have a little so you can analyze it. You can just give it the file name and it will be analyzed. And you can see here the decoding. So you receive, this is the first byte, it is recording device 1 to specific. This is the header. Then you get the command itself, give me the CEC version. Here is the reply. It tells you what the time is between the transmit and the reply. And again, this is basically what you've received. So this is per byte that you get, and then at the end you see a decoded version, which is human readable, which says CEC version command, and that it sends CEC version 2. You can also use the verbose option, and then you see every transition on the bus, exactly timestamps. So here you can really drill down to the lowest level of the bus. And if you look at, for example, what was it, on low drive, I think. Let me see. So this is what happens when you don't send an adult message. And you see you will get a nice warning. It says, hey, I'm missing something. So it will warn for these various conditions on the bus. Also if you, sorry, that is to a short bit. So it will actually warn, you can see that here, it says, hey, data bit 2 is too short. So you can use this to get a really good view of what is happening on the bus, what if those devices respond correctly to various errors. And this has actually been very productive. We've used this with actual products that did the wrong thing, and we managed to figure out what was going on. In that particular case, we had a CEC controller that would just occasionally stick, the bit was stuck for 5 milliseconds, either at 0 or 1. And it turned out that that had to do with the microcontroller that could get into a wrong state for a while when it was missing an interrupt. So we could actually prove that it was not on our side, but it was on the other side. All this for less than $100 bucks. I was very pleased with it. It's been extremely useful, otherwise you need to buy really expensive devices for that. Some resources. The CEC protocol, it is available in the HDMI 1.3 specification, which is free. The 1.4 has some changes. Let me put it this way, if you Google, you can probably find it. The HDMI 2.0 is completely enough. You need to pay for it. There are not that many differences between 1.4 and 2.0. The framework has been made for 2.0. Documentation, these are the utilities. I keep log status information, so if you want to know what the current status is, you can look here. My email and the final pitch, if anyone is interested to volunteer for some media subsystem projects, I have made a wiki link at the bottom where I have lots of projects. So if you're interested in doing some kernel development or some development for utilities, take a look there. That's it for me. Questions?
All this stuff looks very interesting from the technical point of view, but I suspect it may not work as expected. And I don't think it's valuable on the current market. Please give your opinion. Is it still valuable? Is it worth to invest in the development of such interface?
It's actually used more and more. So for certain features like audio return channel, it's compulsory. Actually, it's improved a lot. So in the past, what happens is that, say, Samsung would come out with a high-end TV that was supporting this, but it would only work well with their own video receiver, with their own player, which defeated the purpose, because it's meant to be as a general way of communicating. These days, it's much better, because customers got wise and they said, still working? Yeah. If I buy a Blu-ray from Samsung and a TV from LG, I want them to be able to communicate. It's actually improved a lot. Not perfect yet, but interoperability is much better than it used to be. And yeah, it's used. It's still heavily used. Actually more than in the past. And all the the little SIM-port computers that you can buy that run Kodi, they all are able to use this. And Kodi is actually actively investigating using this framework to replace the old libCEC implementation.
Actually, from a quick glance, it looks like a try to unify a smart home or so, how it works. Good. Isn't it?
It tries to what?
It's try to unify a smart home. There are a lot of smart home systems, and some vendors try to uniform the interfaces, and they're not working altogether.
This has nothing to do with smartphones. It's just
I know.
It's basic control between different devices. Don't expect that you can fully control another device. It's just basic stuff that you can do.
What level of control should we expect? How basic is it?
Well, from feature sets, really, that's pretty much what you can expect. So the usual consumer things like setting up a timer, recording, tuning. If you want to go into a specific menu to do some settings for a device, that will not work. So it's when it works for what it does, it works pretty well. But it's a very specific use case, this think home theater. Think controlling everything with one remote. That's sort of what we're looking into.
What is the current limitation for the transfer rate for this 400 bytes per second? And is there any way to increase it?
Sorry, is there anyone looking to increase it or?
Current limitation, why the transfer rate is limited by...
Oh, why it is historical. It comes from the old SCART connector, and they just took the whole electrical protocol from there, and that's 400 bits per second. It's just unchanged from technology 20, 30 years old. I was a little kid when they made a decision. I don't know. I was not involved.
Okay, so a comment to your question, is CEC used? Yes, it is. I made a YouTube player with Raspberry Pi, and I can control this Raspberry Pi with the remote control of the TV, and it works out of the box. Thank you.
Interesting presentation.
Thank you.
I have one question regarding one of the first slide. It's CDC packet structure. It doesn't mention error bit detection, no CRC on the slide.
There isn't.
So it's possible that sender will send message, it will be distorted, but still valid message at the receiver.
Yeah.
And it will trigger some errors.
Yeah.
Okay.
Basically, you could say that the way they do error correction is just by being very, very strong.
Second question is regarding the capabilities. You mentioned that logical address describes is a nickname for the device. But in the same time, it's structured like capabilities of the device. On the other hand, there is a slide that mentions that it's not required to implement all capabilities on the video player, for example. Is there something like an enumeration protocol when you can get what capabilities is supported, but from what device?
So first of all, you're right. A logical address is a horrible mix between a nickname and a functionality description. You know, you say your playback device and you have a number of nicknames to choose from. So it's a strange mix. You would never design it like that today. Regarding feature, there are some messages that will give you some feature sets. In CEC 2.0, it is a bit more advanced. You can get more features out of a device, but almost nobody supports 2.0. I have yet to find a TV supporting 2.0. We do, because when I made this, I just went with the latest version. But it's very rare. But it allows you to get more features, more capabilities.
Thank you for your answers. And one more last question. Is there a compiled database of what device support, what capabilities based on your tools? Can they then basically send automatic reports to somewhere?
So short answer is no. The longer answer is I wrote a compliance test. Primarily, initially, for our use case, which pretty much does what you want. So you can just run it against the display and you will get a list of what works and what doesn't. But we wrote it for what we need. So while it does test all the CEC commands, it will only do in-depth testing for those that we actually need. So if you want to test tuning, for example, it is very limited what we test. Patches are welcome. So ideally, you want to have a compliance test that tests the full set in depth, and you just run it against the TV, and you will get a scorecard that is working and that is not, and then you can make a database or whatever. But in order to do that right, we would need people to contribute to the compliance tests and add more tests. Right now, it is for what we need. And not what, say, a Raspberry Pi would want to use. I saw a question, yeah, oh, sorry.
I have gone to, yes, CEC works. I have Samsung TV and Xbox, and I control it with TV pilot, so it works perfectly. And my question is, what kind of CEC commands are? Are there commands like volume up or shut them down, or what they are?
It would take too long. The easiest way to find that is just to download HDMI 1.3 specification, and it contains a pretty complete list of all the features. It would take too long to discuss that here. But you can find it online. Just download it and look at the feature set.
Yes, I have a question. I played with CEC on my Raspberry Pi. I have plugin first and it works fine. But I have a question, is there an integration of this CEC framework to some desktop environments? It will be good to use it, for example, when I play YouTube from my laptop, to use remote from my TV and press play and stuff.
So, the main use cases for something like this would be applications like Kodi that do set up a home theater for your system. They're the main users for this. You can use it yourself, but then you're on your own. I don't have any, but it's fairly easy. You can use these utilities to script things. You can do quite a lot, I think, if you're interested. But there's no standard thing. Last question. Oh, we have another one. Nice to get so many questions, by the way.
You mentioned
that to keep bus timings correct, you should have something like real-time kernel. However, it works even with well, your common kernel. But how is it the most convenient way to do this in commercial devices? Is it ASIC or is it some software?
My real-time commands was specifically to using GPIO as in this system. This is mainly used for testing. The only SoC I know that does it like that is an all-winner A10, A20 SoC. They use a similar mechanism and they cannot be made 100% reliable because of that. So they're 99.9% reliable, but if you start a parallel compile on your box and you expect that the CEC also works perfectly at that time, you get timing errors. But most implementations, they are done in hardware. So the timing is done in hardware and you do not have these problems. You do not need real-time Linux. Even on the all-winner, you don't really need it because the error rate is really, really low. I was able to make it surprisingly good, but I cannot guarantee it for 100%. Okay, thank you very much.